Hi, afternoon, folks. Let me take you through the first topic we have, which is data for AS or A-level computer science. I hope you will find some of the explanations meaningful. All right, there we are. The first problem, we are interested in a conversion from is what binary to decimal. So what we'll do, like we did earlier, we need a scale 1, 2, 4, 8, 16, 32, 64, 128, 256. It keeps on going like that. Then we try and map the this that we have there, then here is 0, 0, 1, 1. So in essence, I have got 128 plus 64, so that's 128. Let me write it properly, 128 plus 64, because I'm targeting where I have 1 plus 8 plus 2, that's 10 plus 15 there. So it's simply plus 15, which will give us 207. So it looks like this will take us to 207 in base 10. Convert 155 to binary. I mean, we use the same scale, 1, 2, 4, 8, 16, 32, 64, 128, 256, we won't reach there. So you can start by putting a 1 there and need our calculator to say we have 155, we subtract 128. So 155 subtract 128, it gives us, well, divide, we want to subtract 155, subtract 128. The result is 27. 27. So here we have a 0, 0. So we subtract 16. Then when we say minus 16, what do we get? 11. So 11. So it means we need a 1 again there. We'll subtract 8. So it gives us 3. 3. Well, this is bigger than 3. So we have then 1, 1, that's 3. So in essence, that's my number here in base 2. Right, next I'm interested in converting this number to its equivalence in binary. So binary, I'll be interested in coming up with uh, A. What's A? A is 10. So let me try and check what we have, because I'll play with 4 bits. So A, let me have 1, 2, 3, 4. So this is 1, 2, 4, 8. So if I want A, which is 10, it means I need these 2 bits. So it will be 1, 0, 1, 0. That's A. Then if I want F, obviously F is strictly all ones, base 2. That's my FA in base 2. Then the next problem, I'm required to find 2's complement of that number. So what I'll do is I'll just invert all the bits, then I'll add a 1. So in doing so, I'll have 1, 1, 0, 1, 0, 0, 1. But then we are saying let's add 1. So if I add 1 there, the result is 0 carry 1. Then I'll have 1, 0, 1, 0, 1, 1, 1. There's 2. That's 2's complement of that value. Then the next problem I'm required in to do binary addition. So I have 1, 0, 1, 1, 0, 1, 0, 0. Then the other value is 0, 0, 0. I have 1, 1, 1, 0, 1. Now I'm adding. So when I add there, I get a 1, 0. There I'll get 0. And there I'll get 0. And there I'll get 1, carry 1. And there I'll get 0. I have 1, I have 1. So that's my solution there. Let's see. Next, I'm interested in looking at the difference between ASCII 2 and Unicode. The difference is that in ASCII we have a fewer number of characters, and this one it caters almost to universal languages, Chinese, German, you name them, they are covered by ASCII. What else can we talk about here? Basically, that's what we have. That's the main difference in that all the characters they are encompassed, and in ASCII is just a fewer characters. And we can talk about bits like 128 bits. It uses 7 bits and it can keep around 128 characters. That's ASCII. but universal code, I mean, there are plenty of characters. Actually, all the world languages they are covered. Explain why extended ASCII2 was developed. I mean, this was developed to just cater for special characters like it, uh, exclamation marks, you name them. Those were the main purpose of coming up with ASCII2. Then here we are interested in the storage of this given value. So the storage is going to be 200 multiplied by 150 multiplied by 8. So get our result in bits and we divide it by 8. It gives us bytes and we keep on doing our calculations like that. So that was 200 multiplied by 150 multiplied by, thought it was 8. Let's double check. Yeah. And when we divide this value by 8, let's divide by 8, it gives us 30,000 bytes. So that's 30,000 bytes. But when we divide again by 1,000, it turns to kilobytes. So this is just 30 kilobytes. Right. Moving on, explain the effect of reducing sample rate from, well, because we are reducing, size is reduced. That's one. It's more to do with compression. Uh, so, yeah, basically size that we can classically mention. Then we move on to number 10. Apply RLE to what we have here. So we have got 4p, so that's 4p and 2q. And then we look at that, that's 5r. When we look at the product, at 3s. I think that's it on the first part on data for A-level computing science. Thank you.